Someone wise once remarked, "The cosmos is the grandest art gallery imaginable." It's a statement that's hard to argue with, especially when you gaze at the breathtaking vistas captured by our telescopes, swirling galaxies, shimmering nebulae, and stars blazing in every hue of the cosmic palette. The universe is a sprawling masterpiece, vast beyond comprehension, endlessly stretching into the unknown, shattering every boundary our minds can conceive. It's a place of awe, mystery, and relentless beauty. But like all things, even this grand exhibition must one day draw to a close. Imagine a future so distant it dwarfs every apocalyptic blockbuster Hollywood has ever churned out. Picture a universe where the last living stars have flickered out, their radiant flames extinguished. No new stars ignite in the void. Creation has stalled, the cosmic nursery long since abandoned. What remains is a desolate expanse dotted with black holes of every size and mass, silently evaporating into nothingness through the eerie quantum magic of Hawking radiation, a process where these gravitational titans leak particles into the abyss. The once vibrant tapestry of the cosmos has unraveled, leaving only shadows of its former glory. And what of the stars that once painted the night sky with light? Their remnants linger as white dwarfs, dim, cooling husks of what they used to be. Gone are the majestic constellation, the glowing clouds of gas and dust, the radiant beacons that guided ancient dreamers. Darkness creeps in, an unyielding tide that seeps into every corner, swallowing the universe whole. It's a somber scene, a requiem for infinity. But hold that thought. Let's not linger in the gloom just yet. Instead, let's rewind and explore the fascinating characters in this cosmic drama, the white dwarfs. White dwarfs are the retirees of the stellar world, and they've got quite a story to tell. If you've ever tuned into our videos, or if you're new here, welcome aboard. You might recall we've covered these celestial relics before. Stars, you see, are not static. They evolve, their fates dictated by a key player, mass. A star's mass determines whether it'll exit the stage with a bang or fade away with a whisper. Take stars like our sun, modest yellow dwarfs that don't quite qualify for the heavyweight division. These stellar middleweights spend their lives, about 11 billion years for the sun, quietly fusing hydrogen into helium, a slow burn that sustains their glow. But even the steadiest candle eventually gutters. When the fuel runs low, these stars swell into red giants, their outer layers puffing up like a cosmic balloon. Think of Aldebaran, the fiery eye of Taurus, a red giant familiar to stargazers since childhood. Then, in a dramatic finale, they shed their outer shells and collapse inward, compressing into a dense, glowing ember, a white dwarf. Let's zoom in on a real-life example. Sirius B, the nearest white dwarf to Earth, a mere 8.6 light-years away, practically next door in cosmic terms. Once a robust star, Sirius B shed its outer layers some 120 million years ago, leaving behind a core no larger than Earth, but packing a mass close to the Sun's. It's a stunning transformation. A star that once blazed brightly, now reduced to a faint, shrinking spark. Structurally, a white dwarf is a marvel, a ball of electron-degenerate matter, a soup of plasma so dense that a teaspoon of it weighs as much as an elephant. Without a fusion furnace to keep it warm, it cools slowly, radiating its leftover heat into the void. But the story doesn't end there. Given enough time, trillions of years, mind you, a white dwarf might fade further, transitioning into a black dwarf. These enigmatic objects barely glow, if at all, their light too feeble to pierce the darkness. For years, astronomers thought black dwarfs were the final chapter for stars like these, the ultimate endpoint of stellar evolution. But hold your telescopes. There's more to this tale, and we're about to unravel it. Black dwarfs are the underdogs of the cosmic cast, elusive and misunderstood. Unlike their white-hot predecessors, they emit little to no visible light, making them ghostly figures in the universe's lineup. A key condition for their existence is the absence of accretion. No more siphoning gas or dust from their surroundings to fuel their glow. They're cut off, left to cool in isolation. Here's the catch. You won't find black dwarf plastered across scientific journals, and no, it's not because of some interstellar conspiracy. It's simpler than that. Our universe, at roughly 13.8 billion years old, is still a spry youngster by cosmic standards. White dwarfs take billions of years to cool to the frigid temperatures, around 5 Kelvin, just above absolute zero, needed to become black dwarfs. The coldest white dwarfs we've spotted hover around 4,000 Kelvin, still too toasty to cross that threshold. In short, the universe hasn't had time to churn out a significant population of black dwarfs. They're a future phenomenon, a preview of what's to come. But what will come? The universe isn't an endless well of star-making material. Interstellar gas, the raw stuff of creation, is finite. As it dwindles, star birth will cease, and the slow march of cooling white dwarfs will give way to a new regime, the age of black dwarfs. These objects have a mass ceiling known as the Chandrasekhar limit, about 1.4 times the Sun's mass. It's the tipping point where the pressure of degenerate electrons balances gravity's crushing grip. Beyond this limit, a star's fate veers toward neutron stars or black holes. But for black dwarfs, this boundary sets the stage for some wild possibilities. Black dwarfs might seem like the end of the line, but the universe loves a plot twist. These cold, quiet relics could have a few tricks up their sleeves, depending on forces like dark matter and quantum quirks. Let's explore two jaw-dropping scenarios for their distant future. In the first act, black dwarfs might tap into dark matter, if it exists, to prolong their twilight years. Picture them as cosmic scavengers, sipping on this mysterious substance to stave off oblivion. But even dark matter can't stop the clock forever. Protons, the building blocks of matter, face an existential dilemma: decay or endure. If protons decay, a big if in physics, black dwarfs could unravel over an unimaginable timescale, a decillion years, that's 10^3 years, a number so vast it's a 1 followed by 33 zeros. As they decay, these dwarfs transform into iron-56, a stable isotope, becoming what astronomers call iron stars. These metallic husks could linger for an eternity, think 10^76 years, a 1 with 76 zeros, before collapsing into black holes under their own weight. From there, Hawking radiation takes over, evaporating them over an unvigintillion years, 10^66. It's a slow, drawn-out exit, a cosmic tragedy stretching across eons, not exactly a blaze of glory, but a fittingly quiet end for such understated players. Now buckle up for the second act, because this one's a showstopper. Quantum mechanics throws a curveball with a phenomenon called quantum tunneling, where particles sneak through barriers they shouldn't be able to cross. Inside a black dwarf, this could spark spontaneous nuclear fusion, even without the energy to sustain it. Over countless millennia, fusion products pile up, choking the dwarf's core until it can't take it anymore. Then, bam, a black supernova erupts. Unlike the dazzling supernovae of massive stars, which birth neutron stars or seed new stellar nurseries, this explosion is a swan song. Only about 1% of black dwarfs, those near the Chandrasekhar limit, might pull off this feat. It's a rare, cataclysmic encore, a final flare in a universe grown dark and cold. These blasts could be the last fireworks in the cosmic sky, signaling the end of an era. Step back and take it all in. Imagine a universe where black dwarfs dominate, relics of a time when stars ruled the heavens. The once bustling cosmos fades into a wasteland of silence and shadow. Regular supernovae leave behind legacies, neutron stars, black holes, or the seeds of new stars, but black supernovae. They're the endgame, a final gasp before the void claims everything. Ice and darkness reign supreme, an all-consuming stillness that blankets infinity. It's a chilling vision, but don't despair just yet. These are hypotheses, cosmic what-ifs based on our best calculations. And here's the kicker. This fate won't unfold for something like 10,000 years. A Googleplex, a number so absurdly large it defies imagination. Humanity has plenty of time to chase its dreams, explore the stars, or, let's be real, bicker its way into oblivion. Either way, the universe's grand finale is a long way off, so why not marvel at the journey instead? Let's lighten the mood with a detour through the universe's gallery of wonders. First stop, the Sombrero Galaxy, a spiral beauty in Virgo, 29 million light-years from Earth. Its elegant disk and glowing bulge hide a secret, a supermassive black hole weighing in at 1 billion solar masses. Next, meet NGC 1277, a compact lenticular galaxy in Perseus, 220 million light-years away, packing a black hole 17 billion times the Sun's mass. And then there's Holmberg 15A, a colossal elliptical in Cetus, with a central beast estimated at 10 billion solar masses. These galactic titans share a common trait. At their hearts lurk supermassive black holes, gravitational juggernauts shaping their domains. We've cataloged dozens of these monsters, each a testament to the universe's penchant for extremes. But how did they get so massive so fast? Some formed less than 1 billion years after the Big Bang, a puzzle that's kept astronomers scratching their heads. To crack this mystery, let's travel back to the universe's infancy, when the first stars, population 3 stars, ignited. These pioneers were forged from primal hydrogen and helium, with no heavier elements to complicate their chemistry. They were giants, hundreds of times the Sun's mass, burning hot and fast. Within 1 million years, they exhausted their fuel, exploding as hypernovae and collapsing into black holes, seeds for something bigger. But what if some didn't collapse outright? Enter the quasi-star, a hypothetical behemoth unlike anything we see today. Not to be confused with quasars, those blazing beacons powered by black holes. Quasi-stars were massive stars with a twist, a black hole core. Picture a star 10 billion kilometers wide, over 1,000 times the Sun's mass, shining 100,000 times brighter. Compared to titans like Scuti or Stephenson 2-18, quasi-stars were cosmic colossi. Their black hole hearts devoured their interiors, growing into the supermassive monsters we see today. It's a wild theory, but it might just explain the early giants lurking in galactic cores. We're just beginning to sketch humanity's chapter in this vast saga. We've decoded much about the universe, how stars live and die, how black holes warp reality, but countless mysteries remain. The origins of supermassive black holes are a tantalizing riddle, one of many we'll tackle in time. For now, let's revel in the spectacle, a universe brimming with wonders, from fading dwarfs to galactic heavyweights, all part of an epic unfolding over billions of years. So what's next? Hit that thumbs up, subscribe if you haven't, and ring the bell for more cosmic adventures. The universe isn't done with us yet, and neither are we. Until next time, keep your eyes on the stars. Imagine a star so colossal it could swallow our solar system whole, stretching its fiery tendrils far beyond Pluto's lonely orbit. Picture a behemoth with the mass of a small globular cluster, a bustling congregation of stars, and a brilliance rivaling that of a modest galaxy. This, my friends, is a quasi-star, a celestial titan that defies everything we know about the twinkling lights above. Its surface temperature, a sizzling 10,000 Kelvin, might not sound jaw-dropping at first blush. After all, it's only about twice as hot as our sun. But don't let that fool you. This isn't your average stellar neighbor. This is a cosmic enigma, a star with a secret so wild it rewrites the rules of the game. What sets quasi-stars apart isn't just their gargantuan sishipikish. It's what lurks within. Typical stars, like our sun, have cores, where nuclear fusion churns out energy, fusing hydrogen into helium in a fiery dance that keeps them shining for billions of years. But quasi-stars? They've taken a detour down a darker, stranger path. At their heart lies not a fusion furnace, but a black hole, a gravitational monster that powers the star in a way no ordinary stellar engine ever could. Before you raise an eyebrow, let's be clear. Quasi-stars are purely hypothetical. They're the stuff of scientific speculation, dreamt up to solve some of the universe's biggest mysteries. Yet their story is so tantalizing that astronomers can't help but wonder, could these giants have once roamed the cosmos? Not long ago, scientists began eyeing quasi-stars as potential ancestors of the supermassive black holes we see today, those titanic voids at the centers of galaxies, with masses stretching into the billions of suns. To understand how they might come to be, let's rewind to the universe's wild, youthful days, when chaos reigned and the seeds of creation were just taking root. Picture vast clouds of gas, swirling soups of hydrogen and helium, drifting through the primordial void. These are the cradles of stars, where gravity starts its slow, relentless work. From these clouds emerge protostars, awkward, embryonic blobs that haven't yet found their footing. They're not hot enough to spark fusion, not yet full-fledged stars, but they're growing fast, gobbling up gas and dust from their surroundings, rounding out into spheres as they bulk up. Most protostars follow a familiar script. Their cores heat up, pressure builds, and eventually fusion ignites, birthing a star like our sun. But for a select few, those rare, oversized oddballs, things take a dramatic turn. If the center of one of these massive protostars collapses under its own weight, it doesn't just fizzle out. It forms a black hole. Now, you might think, wait a second, a collapse into a black hole? Wouldn't that blast the whole star apart, leaving nothing but a cosmic mess? Fair question. In a typical stellar demise, that might be true. Think of a supernova shredding its outer layers into a dazzling nebula. But quasi-stars are different. Their sheer mass is their shield. Even as their core implodes into a black hole, their outer layers hold firm, wrapped around this newborn singularity like a protective cloak. The black hole doesn't destroy the star, it feeds it. Siphoning matter from the surrounding gas, it radiates heat and energy, keeping the quasi-star aglow. It's a symbiotic relationship, a stellar beauty, with a ravenous beast at its core, sustaining each other for about 7 million years. To keep this cosmic duo humming, the black hole has to eat big, about 14% of the sun's mass every year. That's a feast of gas and dust, funneled into an accretion disk that spirals inward, glowing fiercely as it's devoured. But all stars, even the strangest ones, have an expiration date. When the quasi-star's outer layers finally thin out, or the black hole's appetite outstrips its supply, the star dies, leaving its dark heart exposed. What remains is a black hole, a seed that, over eons, could grow into a supermassive giant, anchoring a future galaxy. It's a mind-bending origin story, one that might explain how those monstrous black holes appeared so early in the universe's history. But here's the rub. Quasi-stars are as elusive as a whisper in a storm. They're hypothetical for the same reason Population 3 stars, the universe's first generation of stars, are hypothetical. Born in the raw, unpolished aftermath of the Big Bang, these ancient stars were made of the lightest elements, hydrogen and helium. With no metals to spice up their chemistry, they grew to sizes we can barely fathom, hundreds or thousands of times the sun's mass, burning hot and fast before exploding in spectacular fashion. Their lifespans were short, mere cosmic blinks, so finding evidence of them today is like hunting for a ghost in broad daylight. Quasi-stars, if they existed, would have been even rarer, fleeting anomalies in an already chaotic epoch. Could protostars really pack enough punch to become quasi-stars? Modern observations throw a wrench into the idea. Clouds with less than 1 million solar masses of material tend to birth supermassive stars. Huge, yes, but not quasi-stars. These stars might collapse into black holes too, but they lack that bizarre black hole core twist. Our understanding of star formation is still a work in progress, a puzzle with missing pieces. Yet the quasi-star theory lingers, a compelling what-if, in the quest to explain the supermassive black holes powering distant quasars, those blinding beacons trillions of times brighter than the sun. Maybe the biggest stars we've yet to discover hold the key. Now let's twist the script a bit. In videos about mega objects, we often ask, what if this thing replaced the sun? It's a classic thought experiment. Plug a giant into our solar system and watch the chaos unfold. But let's mix it up. Imagine a quasi-star doesn't replace the sun, but barges into our neighborhood, strolling in from Neptune's direction. What happens next? First off, we'd spot it long before it crashed the party. A star that bright, that massive, would light up our skies like a second dawn, growing more dazzling with every passing day. Telescopes would buzz, social media would explode, humanity would be transfixed. But this isn't a feel-good visitor. As the quasi-star barrels into the solar system, its gravity would wreak havoc. Planets, asteroids, comets, everything would be flung from their orbits like toys in a toddler's tantrum. Earth wouldn't escape the chaos. Meteoric showers would pepper our planet, a relentless barrage of rock and ice tearing through the atmosphere. The quasi-star's path would bulldoze through the outer giants, Neptune, Uranus, Saturn, Jupiter, disrupting or devouring them as it goes. Closer to Earth, its heat would turn our world into an oven. At 260 degrees C, the atmosphere would boil into steam and carbon dioxide, choking out life. Push the dial to 760 degrees C, and sulfur dioxide would join the mix, a toxic brew straight out of a nightmare. The temperature would keep climbing until Earth's crust and mantle vaporized, our planet reduced to a fleeting snack for the quasi-star's insatiable black hole. In the end, nothing would remain, just a slightly fatter black hole, drifting onward. Grim? Sure. But it's a reminder of the universe's untamed power. If you're as hooked on cosmic wonders as we are, hit that subscribe button and give this tale a thumbs up. We'd love to keep exploring the void with you. See you in the next stellar showdown. Despite mountains of research and terabytes of data, humanity's grasp of the cosmos is still in its infancy. We've cataloged stars, planets, and galaxies, but there's so much more lurking out there. Objects we've only theorized about, some we've modeled on computers, others we've barely dared to imagine. Are they real? Maybe. Maybe not. The point isn't that we're stumbling in the dark, it's that we've only just begun to shine a light. Theoretical predictions have a knack for turning into discoveries. Take Neptune. It was math, not a telescope, that pinpointed its existence. Neutron stars were dreamed up decades before we spotted their eerie glow. Today, we know of thousands of them, and that's just the start. So why not quasi-stars? Or something even weirder, like quark stars? Let's dive into that rabbit hole and see where it leads. Start with neutron stars, the cosmic leftovers of medium heavyweights. Imagine a star bigger than the sun but not quite a titan, say up to 8 solar masses. It lives its life, fuses its fuel, and then when the tank runs dry, it goes out with a bang, a supernova. The explosion paints the sky with a nebula, a shimmering farewell. What's left behind depends on mass. If the core tips past 3 solar masses, gravity wins and it collapses into a black hole. But if it lands below that threshold, say 1.5 solar masses, you get a neutron star. These things are tiny, about 20 kilometers across, the size of a city, but absurdly dense. A sugar cube of neutron star material weighs as much as Mount Everest. In our Milky Way, they're rare gems, 1 per 1,000 regular stars. Their insides are a crush of neutrons, packed so tight that atoms as we know them cease to exist. But what if a star's mass falls into a gray zone, too heavy for a neutron star, too light for a black hole? Enter the quark star, a contender so strange it makes neutron stars look tame. Quark stars double the mystery. The name comes from quarks, the tiniest building blocks of reality. Quick primer: quarks are the Lego bricks of protons, neutrons, and electrons coming in 6 flavors: up, down, strange, charm, beauty, and top, each with quirky traits. Their colors, red, green, blue, aren't about hue but how they interact via gluons, the glue of the subatomic world. Quirky, right? These particles are the bedrock of everything we see, and quark stars might be their ultimate showcase. Here's the gist. Neutron stars are made of degenerate neutron matter, squashed by gravity into a solid mass. But crank up the pressure, say from the star's own weight or the supernova that birthed it, and those neutrons might crack open, spilling their quarks into a soup called quark matter. This could happen just at the core or engulf the whole star, depending on the physics at play. Trouble is, we're not sure how it works. Regular quark matter is high energy, stable only under extreme heat and pressure, like the Big Bang's first moments. A fully quark star might collapse without those conditions, unless, that is, it transforms into strange quark matter. Here's where it gets wild. If enough up and down quarks morph into heavier strange quarks, the energy drops, stabilizing the mix. Strange quark matter might even survive in space's chill, meaning a star made entirely of it could hold together. Spotting one, though? That's the kicker. They look a lot like neutron stars, same size, similar glow, unless their mass stands out. A quark star might tip the scales higher than a neutron star's limit, a cosmic red flag. Theories abound, but evidence, zilch, so far. Most astrophysicists peg quark stars as neutron star cousins, siblings in the stellar graveyard. But there's a twist. Enter Edward Witten, a physics titan, who posits that clumps of strange matter, relics of the early universe, float out there, maybe as dark matter. A massive star snags one, and instead of a neutron core, it births a quark star. It's a long shot, but it's the kind of idea that keeps the cosmic pot simmering. So, where does that leave us? Quasistars, quark stars. They're shadows on the edge of our vision, possibilities waiting to be confirmed or debunked. The universe is a vast, untamed frontier, and we're just scratching the surface. Every calculation, every observation brings us closer to the truth, or to more questions. That's the beauty of it. Stick around, keep exploring, and who knows? The next big discovery might be just a telescope away. Let's conjure up a vision of a star so immense it could engulf nearly the entire solar system, its fiery edges stretching far beyond Pluto's distant orbit. A celestial giant with the mass of a small globular cluster and a radiance rivaling that of a modest galaxy. This is no ordinary star. This is a quasi-star, a cosmic marvel that pushes the boundaries of imagination. Its surface burns at around 10,000 Kelvin, a temperature that might seem underwhelming at first glance. After all, it's only about twice as hot as our sun. But don't be fooled by that number alone. The quasistar's true wonder lies not in its heat, but in its sheer scale and the bizarre secret it harbors within. Unlike the familiar stars dotting our night sky, quasistars don't play by the usual rules. Most stars, like our Sun, rely on a core where nuclear fusion churns hydrogen into helium, a steady engine that powers their light and warmth for billions of years. But quasistars, they've charted a wildly different course. At their heart lies not a fusion furnace, but a black hole, a gravitational vortex that drives the star in a way that defies everything we've come to expect from the cosmos. Before we dive deeper, let's set the stage. Quasistars are purely hypothetical, figments of scientific curiosity rather than observed realities. Yet, their allure is irresistible, offering a potential clue to one of astronomy's greatest puzzles, the origin of supermassive black holes. Not too long ago, scientists began toying with the idea that quasistars might be the ancient progenitors of those colossal black holes, lurking at the centers of galaxies, some boasting masses billions of times greater than the Sun's. To explore this theory, let's travel back to the universe's chaotic infancy, a time when the cosmos was a swirling cauldron of possibility. Imagine vast clouds of gas, rich soups of hydrogen and helium, drifting through the void, untouched by the heavier elements that would come later. These clouds are the cosmic nurseries where stars first take shape. From these gaseous cradles emerge protostars, clumsy and unformed, like dough rising before it's baked. They're not yet stars in the traditional sense, no fusion fires burn within, but they're growing, pulling in more gas and dust, rounding out into spheres as gravity tightens its grip. For most, the path is predictable. As their cores heat up and pressure mounts, fusion ignites, and they become proper stars. But for a rare few, the story takes a darker turn. If a protostar grows massive enough, far beyond the norm, its center might buckle under its own weight, collapsing not into a fusion core, but into a black hole. You might wonder, a black hole, wouldn't that tear the whole thing apart? It's a fair point. In a typical star's death throes, a core collapse often triggers a supernova, blasting its outer layers into space in a dazzling farewell. But quasistars are built differently. Their immense mass acts like an anchor, holding their outer shells intact even as the core implodes. What emerges is a strange hybrid, a star with a black hole at its heart, feeding off the surrounding gas to radiate heat and light. It's a cosmic dance, a radiant giant powered by a ravenous monster, thriving together for about 7 million years. To sustain this odd partnership, the black hole must gorge itself, consuming roughly 14% of the Sun's mass each year. Picture a swirling disk of gas spiraling inward, glowing fiercely as it's devoured, fueling the quasistar's brilliance. But even this strange symbiosis can't last forever. When the star's outer layers dwindle or the black hole's appetite outpaces its supply, the quasistar fades, leaving behind its dark core, a black hole poised to grow. Over unimaginable stretches of time, this seed could balloon into a supermassive black hole, anchoring a galaxy with its gravitational might. It's a bold hypothesis, one that might explain how such titans formed so early in the universe's history. Why do quasistars remain hypothetical? The answer lies in their roots, tied to the elusive population 3 stars, the first generation of stars born in the universe's primal dawn. Forged from pure hydrogen and helium, these ancient giants lacked the metals that pepper modern stars. They swelled to sizes we can scarcely comprehend, burning bright and fast before meeting explosive ends. Their lifespans were fleeting, mere cosmic moments, so finding traces of them today is like searching for a whisper in a hurricane. Quasistars, if they existed, would have been even rarer, brief anomalies in an already turbulent era. Proving their existence is a tall order, perhaps an impossible one. Were protostars ever massive enough to become quasi-stars? Current observations cast doubt. Gas clouds with less than 1 million solar masses tend to spawn supermassive stars. Enormous, yes, but not the black hole-hearted oddities we're imagining. These stars might collapse into black holes too, but they skip the quasi-star twist. Our grasp of star formation is still patchy, a tapestry with threads missing. Yet the idea of direct collapse lingers, a tantalizing what-if, to explain the supermassive black holes powering distant quasars, beacons trillions of times brighter than the sun. Perhaps the grandest stars we've yet to witness hold the answer. Now let's shake things up with a thought experiment. In chats about cosmic giants, we often ask, what if this replaced the sun? It's a fun way to grasp scale. Swap out our star and watch the solar system unravel. But let's tweak the script. Imagine a quasi-star doesn't replace the sun, but gate crashes our system, barreling in from Neptune's edge. What unfolds? First, we'd notice it long before it arrived. A star that massive, that luminous, would blaze in our skies, a second sun growing brighter with each passing day. Astronomers would scramble, headlines would scream, humanity would be riveted. But this visitor isn't here to play nice. As it plows into the solar system, its gravity would upend everything. Planets would wobble, asteroids would scatter, and chaos would reign. Earth wouldn't be spared. The sky would erupt in meteor showers, a relentless bombardment as displaced rocks rain down. The quasi-star would carve a path through the outer planets, Neptune first, then Uranus, Saturn, Jupiter, disrupting or swallowing them in its wake. As it nears, Earth would roast. At 260 degrees Celsius, our atmosphere would boil into steam and carbon dioxide, snuffing out life. At 760 degrees Celsius, sulfur dioxide would choke the air, a toxic shroud. The heat would climb until the crust and mantle vaporized, Earth reduced to a fleeting morsel for the quasi-star's black hole. In the end, nothing would remain, just a slightly heftier black hole drifting on. Dark stuff, right? But it's a glimpse of the universe's raw power. If you're hooked on cosmic tales like this, smash that subscribe button and toss us a thumbs up. We'd love to keep exploring the void with you. Catch you in the next stellar saga. Despite stacks of papers and terabytes of data, our knowledge of the cosmos is a mere speck in the grand scheme. We've mapped stars and galaxies, but countless mysteries linger, objects we've theorized, modeled, but never seen. Some exist on paper, others in wild what-ifs. Does that mean we're clueless? Hardly. It means we're just getting started, peering into a universe brimming with secrets. Theoretical leaps often pave the way for discovery. Neptune was a math problem before it was a planet. Neutron stars were predicted long before their pulses lit up our detectors. Now, we've tallied thousands of them, and that's just the tip of the iceberg. So why not quasi-stars? Or stranger still, quark stars? Let's dive into that cosmic riddle and see what shakes loose. Picture a neutron star, a stellar remnant born from a medium heavyweight, say up to 8 times the sun's mass. It lives its life, burns its fuel, and then explodes in a supernova, leaving a nebula as its farewell gift. What remains depends on mass. If the core tops 3 solar masses, it collapses into a black hole. But if it's lighter, around 1.5 solar masses, it becomes a neutron star. These are tiny, just 20 kilometers across, but pack a punch. A teaspoon of their matter, weighs billions of tons. In our galaxy, they're rare, 1 per 1,000 regular stars, crushed neutron husks glowing faintly in the dark. But what if a star's mass lands in a murky middle ground, too heavy for a neutron star, too light for a black hole? It's a cosmic limbo, neither here nor there. That's where quark stars step in, strangers even among the strange. They're twice as mysterious as neutron stars, named for quarks, the tiniest Lego bricks of reality. Quick rundown. Quarks build protons, neutrons, and electrons coming in 6 flavors: up, down, strange, charm, beauty, top, each with its own flair. Their colors, red, green, blue, aren't hues but quantum quirks tied to gluons that bind them. These specs underpin everything, making quark stars a tantalizing prospect. Here's the scoop. Neutron stars are dense neutron blobs, squashed by gravity into a solid mass. Ramp up the pressure, maybe from the star itself or its supernova birth, and those neutrons might split, spilling quarks into a soup called quark matter. This could stay confined to the core or swallow the whole star, depending on the physics. Problem is, we're not sure. Regular quark matter is high energy, stable only in extreme heat and pressure, like the Big Bang's early chaos. A pure quark star might unravel without that, unless it flips to strange quark matter. If up and down quarks morph into heavier strange quarks, the energy drops, stabilizing the mix. Strange quark matter might endure in space's chill, meaning a star made of it could hold steady. If it converts fast enough, spotting one? Tricky. They'd mimic neutron stars, size, glow, unless their mass betrays them. A quark star might outweigh a neutron star's limit, a cosmic giveaway. Yet here's the kicker. Most scientists aren't ready to toss the quark star idea into the cosmic trash bin. They're optimists at heart, betting that these elusive stars are out there, waiting to be unmasked. They envision a universe where quark stars twinkle faintly, hiding in plain sight among their neutron star cousins. But not everyone's on board. The skeptics, those hard-nosed realists, raise their hands and point out the cracks in the theory. They argue that the leap from neutron matter to quark matter is a leap too far, a bridge we haven't figured out how to cross. Physics at this level is a murky swamp, barely explored, and quarks don't make it easy. Think about it. Quarks are the tiniest specks of reality, so small we can't pluck them out and study them solo. They're locked in tight-knit groups, bound by gluons, and teasing apart their behaviors like trying to solve a puzzle with half the pieces missing. Can they even form stable structures, big enough to make a star? Scientists shrug. The math is mind-bending, the experiments are limited, and the answers slip through our fingers like cosmic sand. From an observational standpoint, it's no picnic either. A quark star, if it's out there, would look frustratingly similar to a neutron star. Same size, same faint glow, same spinning dance. Spotting the difference is like trying to pick out a single stranger in a crowd of... If quark stars do exist, they're rare beasts, especially in our Milky Way. They'd occupy a razor-thin niche, sandwiched between the formation of neutron stars and black holes, a Goldilocks zone of stellar evolution where conditions have to be just right. Too light, and you get a neutron star. Too heavy, and it's a black hole. Quark stars would be the picky middle child, demanding a precise balance of mass and pressure. That rarity makes them a needle in the cosmic haystack, a challenge that pushes astrophysics to its limits. Studying quark matter isn't just a step up, it's a leap into a new frontier, a realm where our tools and theories stretch thin. Right now, the evidence is a whisper, not a shout. We've got tantalizing hints, but no smoking gun. That leaves the door wide open, both for believers and doubters. Every theory that says maybe not has as much right to the stage as the ones shouting yes. It's a cosmic standoff, and we're all waiting for the tiebreaker. Maybe it'll come tomorrow, maybe in a century, when some clever astronomer catches a quark star in the wild, its quirks laid bare for all to see. Until then, we're left with questions, and that's not a bad place to be. The universe is a treasure chest of riddles, spilling over with wonders we've yet to crack. There's enough out there to keep curious minds busy for generations, assuming we don't lose the spark to chase them. Reflect on that for a moment. The cosmos doesn't hand us answers on a silver platter. It dares us to dig, to dream, to doubt. Quark stars might be figments of imagination, or they might be lurking just beyond our telescopes, winking at us from the dark. Every candidate that flops, every theory that falters, is a step closer to the truth. We've been wrong before. Pulsars too fast, diameters too small, and we'll be wrong again. But each stumble sharpens our focus, tunes our instruments, and fuels the fire to keep looking. So, where do we stand? Quark stars are a maybe, a might be, a tantalizing what if that keeps the cosmic conversation alive. They're not confirmed, not dénied, just hovering in the ether, waiting for their moment. And that's the beauty of it. The universe is a vast, wild playground, and we're still kids with magnifying glasses, poking at the unknown. Whether quark stars turn out to be real or just a clever idea, they remind us how much is left to explore. The Big Bang's echoes, the quark's dance, the star's secrets. They're all pieces of a puzzle we're only beginning to assemble. Grab a seat, keep your eyes peeled, and let's see where this cosmic ride takes us next. Theories swirl, but proof? Nada. Most astrophysicists see quark stars as neutron star kin, siblings in the stellar afterlife. But there's a wild card. Edward Witten, a physics luminary, suggests strange matter clumps, Big Bang relics, float out there, possibly as dark matter. A massive star snags one, and instead of a neutron core, a quark star is born. It's a stretch, but it keeps the cosmic pot bubbling. So where are we? Quasi-stars, quark stars. They're shadows on the horizon, waiting to be real or ruled out. The universe is a vast, wild frontier, and we're just dipping our toes in. Every equation, every glimpse nudges us closer or deeper into the unknown. That's the thrill of it. Hang with us, keep gazing up, and who knows? The next breakthrough might be just over the cosmic hill. Picture yourself standing on the edge of a cosmic abyss, peering into the vastness of the universe, where mysteries swirl like stardust in the wind. Among these enigmas are quark stars, elusive hypothetical objects that tantalize scientists and stargazers alike. Whether you buy into the theory or not is up to you. It's a personal call, a bit like choosing your favorite flavor of ice cream. But one thing's undeniable: we don't have a shred of concrete evidence to pin down their existence. Not yet, anyway. Still, the idea of quark stars isn't just some wild flight of fancy. It's a thread that could stitch together the chaotic tapestry of the universe's earliest moments, right after the Big Bang, when everything was a roiling sea of quark matter. And that, my friends, is a fact etched in the cosmic ledger. Why do quark stars matter? Imagine them as time capsules, relics, that could unlock secrets from the dawn of creation. Back then, the youthful universe wasn't filled with the stars and galaxies we know today. It was a hot, dense soup of quarks and gluons, the fundamental building blocks of matter. If quark stars exist, they might offer a glimpse into that primordial chaos, a snapshot of a time when the rules of physics were still being written. It's a tantalizing prospect, one that keeps astronomers up at night, dreaming of the day they might catch one in the act. But so far, these cosmic phantoms remain just out of reach, teasing us from the shadows of theory. Over the years, we've had our hopefuls, candidates that seem like they might fit the quark star bill. Take, for instance, a pulsar in the constellation Ophiuchus, some 39,000 light-years from Earth. This spinning stellar remnant, cloaked in a cryptic catalog number, once dazzled researchers with a jaw-dropping claim. It was clocked at 1,122 rotations per second, making it one of the fastest pulsars ever spotted, a quark star perhaps. The idea sent pulses of excitement through the scientific community. But alas, the thrill was short-lived. Closer scrutiny revealed the numbers didn't hold up, and the object's quark star candidacy fizzled out like a damp firework. Another near miss in the cosmic lottery. Then there was another contender, a neutron star so close to Earth it felt almost neighborly in the grand scheme of things. Early observations painted a curious picture. A tiny diameter, somewhere between 4 and 8 kilometers, and a surface zipping along at 108 kilometers per second. Its temperature? A scorching 700,000 Kelvin, hot enough to make you sweat just thinking about it. Scientists raised their eyebrows. Could this be the real deal? But as they zoomed in, the story shifted. The object turned out to be cooler, closer to 350,000 Kelvin, and a bit chubbier, stretching to 14 kilometers across. Those tweaks flipped the script. Not a quark star, but a garden-variety neutron star. Another swing, another miss. The hunt didn't stop there. In 2008, astronomers turned their telescopes toward a pair of supernovae, wondering if these stellar explosions might conceal quark stars within their fiery hearts. The idea was intoxicating. Imagine a supernova giving birth to something so exotic. Then, in 2015, another supernova caught the spotlight, with whispers that it might be a newborn, strange quark star, a rare breed of cosmic oddity. But whispers aren't proof, and despite the buzz, no one's managed to slap a confirmed sticker on these suspects. The evidence cupboard remains stubbornly bare, leaving us with nothing solid to brag about.